Hey guys, Mr. Backenberg here. In this video, we're going to revisit limits. So what we've got is a ball is rolling down a ramp so that its distance s from the top of the ramp after t seconds is exactly t squared feet. And that's essentially what Galileo did as he was performing his experiments. He found that the distance traveled was equal to the time squared. And we're going to use this idea to try to help us find the instantaneous velocity after 3 seconds, a lot like Galileo did with using smaller and smaller intervals of time to give us an approximation of that instantaneous velocity. So what we're going to look at first is an interval that goes from 3 seconds to 3.1 seconds. Now I'm going to take that information and get some ordered pairs based on using this s equals t squared. These are times, so I can plug those times in for t in here to get my s value. So at a time of 3 seconds, if I take 3 and square it, we've traveled 9 feet. And at a time of 3.1 seconds, if I plug that in and square it, I should get 9.61. So if I want to find the delta s over delta t, because that's our average velocity, the change in position, what I'm going to do is subtract those distances. So I'm going to take the 9.61 and subtract the 9, and then I'm also going to subtract the times to get our change in time. So 3.1 minus 3. So across the top, 9.61 minus 9 is 0.61, and on the bottom, 3.1 minus 3 is 0.1. And if we take 0.61 divided by 0.1, then we're going to get 6.1 feet per second. Now, like we said, what Galileo did was he used smaller and smaller intervals to try to help him approximate that instantaneous velocity. So instead of going from 3 to 3.1, what if we went from 3 to 3.05? So we're shrinking that time interval. Now, we're still going to get that 3, 9 ordered pair, because 3 squared is 9. If we use this time of 3.05, when we square that, we're going to get 9.3025. Now, doing the same thing we did, finding that average velocity, taking delta s over delta t, I'm going to take the 9.3025 minus 9 over 3.05 minus 3. So on the top of our fraction, we're going to get 0.3025, and on the bottom of the fraction, I'm going to get 0.05. Now, when we divide that out, we're getting 6.05 feet per second. And if we continued this process, if we went from 3 to 3.01, so as we keep shrinking that interval, what we're going to notice with these velocities that we're getting is it's going to approach 6 feet per second. So based on these experiments we're running, we can guess that the instantaneous velocity would be about 6 feet per second. Now we can actually approach this a little bit more algebraically if we use a limit. So what we're going to do is we're going to do a limit of our average velocity, so delta s over delta t, but we're going to do our limit as t is approaching 3. So remember, that means that our t value is getting infinitely closer to 3, but never actually truly gets there. Now what we're going to look at doing is finding this average velocity on the interval from 3 to t. And remember, we just said that t was getting closer and closer to 3 without actually ever getting there. So as we're building these ordered pairs, remember, we're still using that t squared from earlier. So if I take 3 and square it, that gives me the ordered pair 3, 9. But if I take t and square it, that gives me the ordered pair t comma t squared. Now if I do my delta s over delta t, if I subtract those y values on top, I'm going to get t squared minus 9. And if I subtract the x values on bottom, that's going to be t minus 3. Now what I want you to notice on top is we've got a factorable quadratic. That's a difference of perfect squares. So we can factor that into t plus 3 and t minus 3. And then this is still over t minus 3. Now notice we've got this t minus 3 on top and on bottom, so those are going to cancel each other out. So that's just going to leave us with t plus 3. Now remember, we're doing this limit as t is approaching 3, so as t is getting infinitely closer to 3. So what I can actually do is I could take that 3 and I could plug it in for my t value right here. So if I take 3 plus 3, that's where we're going to get our instantaneous velocity of 6 feet per second at that time of 3 seconds. Now we do have to remember that t isn't actually equal to 3. T is just infinitely approaching 3, so we can treat it kind of like 3 in the sense that we're able to plug that 3 in. So we're using kind of an intuitive way of trying to find this instantaneous velocity right now. So this is a pretty informal definition for a limit at a value of a. So when we write the limit of a function f of x is equal to L as x is approaching a, what that really means is that our function values, those f of x values, are getting arbitrarily close to that L value as our x value is getting closer and closer to that a value. That's going to be it for this video. Thanks for watching.